Hello. Okay, we're gonna have a little go at some of the questions which she sent us. The first one being this one, which is question 4. Question 4. A developer has brought 3 old houses, which are large. 2 of the houses are constructed of brick, and the third is constructed from stone. The developer plans to convert them into smaller dwellings, such as flats or retirement homes. The developer wants to consider ways of providing comfortable, warm, and dry living environments for the well-being and health of the residents. Excellent. Okay, so question 4A says the walls of the house are built with brick, which are 256 millimeters thick and have a U value of 2 watts per meter squared Kelvin. Calculate the thermal conductivity of the walls. So the formula for U value is your U value. Hopefully that's in focus. So U value is equal to K, which is your thermal conductivity, divided by D, which is the thickness of the material. So we know U is equal to 2 watts per meter squared Kelvin. Still in frame, excellent. And D, the thickness, is equal to 265, I'm going to write times 10 to the minus 3 meters, just to keep everything in meters. So we need to rearrange this to find what K is here. So K is equal to U times D, just timesing through by D. So K is equal to 2 watts per meter squared Kelvin times D, which is 265 times 10 minus, that's minus 3, sorry, minus 3 meters, because it's millimeters to meters. So our answer is K is equal to, can I time these two numbers, 530 watts per meter, and meter cancel, so we just got 1 meter Kelvin times 10 to the minus 3. So just neatening that up, we've got K, the thermal conductivity is 530 times 10 to the minus 3 watts per meter Kelvin, which these are the units of thermal conductivity, so that seems right. Okay, so that's question 4A. Okay, ooh, not. Okay, question 2 is the next one which I've got up. So this is 2 sheets of copper and silver of 30 centimeters by 30 centimeters. So I'm just going to draw them real quick. Okay, drawing was not my forte, so forgive me. Look at me go. Okay, so this one's copper, Cu, and this one's silver, which is Ag, a real chemist. So they are 1 centimeter thick, so this is 1 centimeter, and this is 30 centimeters, and this is 30 centimeters because they're square, believe it or not. 30 centimeters. And what else do we know? Thermal conductivity of the silver, so K, I'm just going to call this Ag, which is for silver. K is equal to 406 watts per meter Kelvin, and Cu is equal to 395 watts per meter Kelvin. Okay, so calculate the thermal resistance of each layer and calculate the overall resistance of the bilayer. So we'll just start off with the resistance of the first layer. So let's do the silver layer first. So our formula for thermal resistance are theta, just a general thermal resistance, where theta indicates temperature. So thermal resistance is equal to delta X, so this is your thickness, divided by the area, which we're looking at, times the thermal conductivity, K. So if we just look at the silver bit, we know the thickness, which is 1 centimeter, which we had here. So we can say R theta, I'm going to put a little AG so we know it's silver, is equal to the thickness, which is 1 centimeter. So that's 1 times 10 to the minus 2 meters, divided by A, which that is 30 times 10 to the minus 2 meters squared, because that's the area of this square. I'll actually write A on that, and I'll write delta x equals delta x here. Times K. So K here, we're going to use the one for silver, so K times 406 watts per meter Kelvin. That's right. So this is our thermal resistance, which if we do some nice cancelling of, no, we'll do units in a little bit, but R theta G is equal to, I did calculate this to be like 2.9, so if you just times 3 times 10 to the minus 2 times 3 times 10 to the minus 2 times 406, and then do 1 times 10 to the minus 2 divided by that, you get 2.9, 2.89 times 10 to the minus 4. And what are the units of this? Well, we can have a look at the units here. So we've got meters squared, we've got meters to the minus 1. So one of these cancels with one of these. So that gives us just meters on the bottom. Times by watts per Kelvin. So on the bottom, the units on, let's just put units, is equal to, we got meters on the top. You normally do this like this, you put units like that. So you got meters on the top divided by, we're just looking at these here, so that's meters squared, and this is watts, meters to the minus 1, Kelvin to the minus 1. So this is just from, this is a divide. So these are 1 over meters and 1 over Kelvin. So this is 1 over meters and 1 over Kelvin. We can cancel one of these with one of these, and then cancel this one with this one, and that leaves us with 1 over watts over Kelvin. Sounds confusing, but we can just move this up here and say that units are equal to Kelvin per watt. I encourage you to have a little go at doing the units to just see where that comes from. But yeah, so the units of our resistance are then Kelvin per watt. So that should be our resistance for AG, for the silver. We can do a little trick for the copper one. So if we say that R theta Cu is equal to, well, it's going to be the exact same formula that we used here, but the only thing that's different is K. So we can say that it's the exact same as this, but we just change this 406 to 385. So we can say that's 1 times 10 to the minus 2 meters over 30 times 10 to the minus 2 meters all squared times 385 watts per meter Kelvin, which is our theta Cu is then equal to, I did calculate this, oh sorry, this was actually for copper, so this was actually 2.89 times 10 to the minus 4 Kelvin per watt, and our theta for Ag was 2.74 times 10 to the minus 4 Kelvin per watt. So, oops, I did them the wrong way around. But yeah, okay, so those are your two answers for that one. Okay, so we just finished with, those are the two answers for the thermal resistance definitely plug in the numbers and make sure you get the same as I did, or be confident in the ones that you got. And then we can move on to what's the overall thermal resistance. So if I stick this here, okay. So the overall thermal resistance, if you think about it, similar to circuits, so you've got two layers. You've got one layer here, and you've got another layer there. So a good way to think about this is what happens when you've got one layer on top of the other. Well, you've got heat which is trying to get through one layer. The resistance of both of them put together is going to be the same as adding those two layers together. So we can say that the heat resistance through this whole thing is going to be the resistance of the first one, of the silver, plus the resistance of the copper one, because the heat has to get through the first one and then it forgets what it's just been through and has to go through the second one. So the total resistance is going to be R total is equal to R theta Ag plus R theta Cu. So the total resistance of the bilayer then is going to be what we worked out previously, which was like R total is equal to 2.74 times 10 to the minus 4 Kelvin per watt plus 2.89 times 10 to the minus 4 Kelvin per watt. Because if you're a little, imagine you're like a little warm particle and you have to get from here to the other side, which is what we're calculating the resistance for. You have to go through the first layer, which has this resistance. Then you have to go through the second layer, which has this resistance. So the total resistance you've gone through is the total sum of those resistances. So if you had like 20 of these layers in a row, then your total resistance would be the sum of each of those layers, because you're going straight through them all. If you were going in this direction along all of these, then you would add them in parallel. But I think that's a question which is cut off. But anyway, so that's question 2A, like I think it was the third part of that. Let's have a look at question 2B, which was, what is the U value of this thing? So we know that U values of the composite body, assuming that the heat is flowing across the square faces and the edge effects can be ignored. So this just means going across the faces. Hopefully you're in focus, yeah. So this is going across the faces, and the edge effects can be ignored. So we can think of this as a U total is equal to K total over D total, which is your thickness, and K is your K total. But this is also equal, well, what do we know? We know R total, don't we? So how do we get from R total to U total? Well, this is our resistance. So we know that R total is equal to, and from our previous formula, which we said here, and this is delta X over A times K, we know that R total is going to be equal to, I'm just going to use D for thickness instead of X. So D total over A total times K total, just from that previous formula that we had from this one. So we know what this is. And we can then rearrange this and say, okay, well, we know this bit is this bit. So we can just times here to get what that is, because that's just the reciprocal of this. So the U value is K over D. We know that R total is composed of D over K, So we can substitute that in. So if we have a little look and say that, well, I'm just going to rearrange this for d over k first. So d total over k total is equal to r total times a total. And then we know that the u value is the reciprocal of this. And we know this because we just worked this out. It's the sum of those two, which I never wrote down, but that's 5.62 times 10 to the minus 4 watts, Kelvin per watt. So we know R total. We know A total because that's just 30. I'm pretty sure. So we can say that K total over D total, and look, I've done the reciprocal of this to give us this, is equal to 1 over R total times A total. Okay, that's that one. And we know this because that's this, and we know this because that's this area here. So and that's equal to the u value. That's equal to the u value. Because that's what we want to find out. So u value is equal to 1 over 5.62 times 10 to the minus 4 Kelvin per watt times, I'm just going to write 0.3 meters all squared. And that u value is ridiculously large. It's like 19,800 watts per meter squared Kelvin. That's another good way to make sure that you've actually calculated the u value, is check your units going through here. So here we got 1 over watts, 1 over 1 over watts, which is watts, 1 over Kelvin, 1 over Kelvin, 1 over meters squared, which is 1 over meters squared. So the units work on that. But this is huge, you know, compared to like a I don't know, like insulation in a house, which U value is like 0.3 or something. This is 19,800. But why is it so large? Well, because you've got two conductors. Gold and silver are conductors, so they conduct heat really efficiently, which is the opposite of what you want in an insulator. So if you've got an insulator in a house, you don't want it to conduct any heat, you want to keep the heat in. But these are conductors, so it makes sense that this is super large, because you put heat on it, it'll go away straight away. Like you touch a metal surface, it feels cold because its U value is like super, super high. It conducts really well. So this makes sense in terms of the size of it. Okay, so the next part of that question is assuming the temperature is 25 degrees C on the silver side and minus 15 on the copper side, calculate the heat transfer across the two layers. So this, we need the heat transfer equation, which is, you've probably seen it written like this, is delta Q over delta T is equal to minus K A delta T by delta X. So this is just the generic heat equation, heat flow equation. So we can say, we draw our little diagram again, we've got 25 degrees plus 25 degrees over here, and we've got minus 15 degrees here. You see, sorry for the writing, this is horrible. Okay, so we want to know what the rate of heat transfer is. We don't want to know just the heat transfer, we want to know the rate. I'm going to stop because I'm running out of time. Okay, so we want to know the rate of heat transfer, and this whole thing is the rate, because this is heat, this is per second, so heat per second is the rate of transfer, because rate is just the change over time. So we want to know what delta Q over delta T is, and that's this. So do we know all of these things? I'd say yes, we do. The only thing which we probably need to figure out is K, but we might be able to do that in a sneaky little way. So if we say that we know that delta T, let's start off with the easy ones that we know. Delta temperature is 25 degrees C minus, and then it's minus 15 degrees C, which is nice, that's 40 degrees C, temperature difference. We know that delta X is equal to this thickness here, the thickness of the both of them, so that's 2 centimeters, which is not, well, 2 times 10 to the minus 2 meters. We know A, and we know K total. And I'll tell you why we know A and we know K total and we know delta X, because what we can do is, if we remember from previously we calculated the U value, we knew what we used these three things to calculate the U value. So we can say that the U value was no, I'm going to use R total. So we know R total even is equal to D total over A total times K total. And surprise, surprise, this is just 1 over all of these three things here. I've used D instead of X, but that's completely equivalent to saying delta X over Ka. So we knew our total from before, so we can just sub this in. So if we do the reciprocal of this and we say 1 over R total is equal to Ka over delta X, then we can rewrite the heat equation here as saying delta Q over delta T is equal to this, which is this, minus 1 over R total times delta T over delta X. Just times delta T, sorry. Ignore that. Just times delta T. Because I've substituted in Ka over delta X is equal to 1 over R total. So the heat equation is then changed to delta Q over delta T is equal to minus 1 over R total times delta T. And we know delta T is 40, and we know our total from before was like 5.62 times 10 to the minus 4, so we know that delta Q over delta T is equal to minus 1 over 5.62 times 10 to the minus 4 watt. Kelvin per watt times 40. And that degrees C, so degrees Celsius and degrees Kelvin are the same thing, but just offset from one another. So 1 Kelvin, if you increase something by 1 Kelvin, that's the same as increasing it by 1 degree C. The only difference is Kelvin starts at 0, and degree C starts at minus 273. That's the only difference between the two of them. So you can interchange that and say that's 40 Kelvin. So our Kelvin, our heat transfer then, these units will cancel, these K's will cancel. And our heat transfer should just be in joules per second. So this is equal to 40 minus 40 over 5.62 times 10 to the minus 4. And this is 1 over watts. So 1 over watts is watts. And we know that watts are joules per second. So we can say that this is equal to minus 40 over 5.62 times 10 to the minus 4 joules per second, which is great. Those are the right units. Let me just calculate what that number is real quick, because I don't have that written down anyway. Okay, so it's 40 over 5.62 times 10 raised to the power of -4, which I reckon gives us like 71,000. So this is 71 times, well, we can just say 71 kilojoules per second. That's what I think the answer is. Make sure to double check. That's what I think the answer is. Okay, moving on to the last question. We're in the last question now, I think. Woohoo! So the last question. This one is, we have a metal rod, so this was problem 2. It was described as problem 2. And, calm down pen. We got a metal rod with a length of 0.4 meters. Okay, so here's my fabulous drawing again. So it's got a length of 0.4 meters. It's got a diameter of 0.04. So I'm going to draw this as a bigger circle. So this is the end. I'm going to say this is this. Lovely. And this is 0.04 meters. It has one end here being held at 373 Kelvin, and the other end here is being held at 273 Kelvin. Calculate the total amount of heat conducted in 1 minute, given that K, so we know that time total is equal to 60 seconds. Always do things in seconds if you can. K is equal to, so that thermal conductivity is equal to 385 joules per meter second per degree. Okay, that's a 5. That's a joule. That's a joule. Okay. So what do we know? We want to calculate the total amount of heat conducted. So we go back to our heat equation, which is delta Q over delta T is equal to minus Ka delta T over delta X. This is our heat equation which we're going to use as our base. So if we go over here, we can say, well, we want to know what, not what delta Q is, but what Q is, so the total amount of heat which is conducted in a minute. So the way that we do that is we would normally integrate this. So this is a differential equation, and we would integrate this. But that might sound really complicated, but all it means is you just add up all the bits of energy which are transferred every second. You just add them all up. So we know that this is being held like this for 60 seconds, so we'll just times this equation by 60 seconds to give us the total heat transfer. I'll put that another way, maybe we can understand better. But yeah, so we want to know what Q total is, and we can rearrange the equation to be Q tot is equal to T tot, so these are totals, it's equal to minus Ka delta T over delta X. So Q total is equal to minus Ka delta T over delta X times T total. T tot. So Q tot is equal to this, which is minus, and it's 385. I'm going to put all the units in as well. This is going to be lovely. Joules per meter second degree. Okay, I decided to get a new piece of paper and do this all on one line because it's quite a long calculation with all the units in. So we've got Q tot is equal to minus Ka delta T over delta X. Focus please. There we go. T tot which is equal to minus 385 joules per meter second degree C times, now what is A in this situation? A is the area of that rod. So that's the area of this circle at the end here. Fabulous. And the area of this, A, is equal to pi r squared. R is equal to 0.04 divided by 2 meters. So that's the area of this, because that's the area in which the heat is being conducted. So that's pi times 0.02 meters all squared times delta T was, so if I write up here delta T, well I'll actually write A is equal to pi r squared times 0.04 over 2 meters squared. Delta T is equal to 373k minus 273k, which is a lovely 100k. Beautiful. And delta X is the length over which the heat is being conducted. We were told that it was being conducted over the entire length of the rod, so it's going along here. That's where the heat's going. Well, it's actually going from the hot end to the cold end, so it's going this way. And delta X is 0.4 meters. So delta T is 100k times 100k over 0.4 meters times, and T tot is 60 seconds. So it's 60 seconds. Now I'm going to deal with the units first. So I think that's a really good thing to sort of get your head around. So heat being transferred, total heat transferred. Have a think about what units you think that would be in first. So maybe have a pause, have a think what units it would be in first. And I'll tell you the answer now. So heat being transferred is going to be in joules. So we want to make sure that this all makes sense and that we get joules. So we currently have joules here, which means all the other units must cancel somehow. So we've got meters to the minus 1. That cancels with one of these meters. So I'm just going to, yeah. And then we've also got meters divided by meters here, which cancels with the other meter. So those two and that one, all the meters cancel. We've got seconds and 1 over seconds, so they cancel. And then we've got Kelvin and 1 over degree C, which we know 1 Kelvin is 1 degree C, so they cancel. And we're left with just joules. Fabulous. So we know that our answer then is minus 385 joules. Ah, no, I'll write that right at the end. Minus 385 times pi times 0.02 squared times 100 over 0.4 times 60 joules, which, let's see if we can calculate that. Let me just get my calculator. So that's minus 385 times pi. I'm gonna put pi at the end. No, it's physics, isn't it? Not maths. Times 0.02 times 0.02 times 100 divided by 0.4 times 60. We get minus 7,260 joules. That is what I think the answer is for the amount of heat which was transferred in a minute.